For thousands of years, humanity has gazed at the night sky, trying to unravel the mysteries of space. The light of distant stars beckons and mesmerizes, promising to reveal the boundless expanse of the universe. Each new discovery pushes us to the realization that we are only beginning to understand how vast and mysterious our cosmos is. But what if you learned that beyond our planet lie even more unimaginable secrets than you could ever imagine? Some of these facts about space are so astonishing that they seem like science fiction. Imagine a star emitting light brighter than hundreds of thousands of suns, or a planet where it rains glass. Scientists continue to study these phenomena, trying to understand their nature and causes. Such discoveries often overturn our understanding of the universe and show that even our boldest notions about space may not be ambitious enough. However, it's not just the extreme conditions and astonishing natural phenomena that make space so captivating. It turns out that even in the apparent emptiness of space, true wonders can hide, from invisible black holes to mysterious signals from distant galaxies. What else might await us beyond our planet? Space has always been one of the most mysterious and captivating areas of human research. Within its boundless expanse lie many secrets and mysteries that we are only beginning to unravel, thanks to modern technology and scientific achievements. One of the most exciting aspects of space exploration is the study of star and planet formation. In this context, protostars like L1527 represent unique objects for observation and analysis. L1527 is a young protostar in the process of formation, providing scientists with the opportunity to observe the stages that stars go through in their early existence. These studies not only satisfy our curiosity, but also help us understand fundamental processes occurring in the universe. A key tool for studying such protostars is the ALMA, Atacama Large Millimeter Submillimeter Array Radio Telescope. Located in the Atacama Desert in Chile, ALMA is one of the most powerful telescopes in the world designed to study cold and distant regions of space. ALMA consists of an array of 66 antennas, each of which can be moved and reconfigured to create various arrangements. This allows the telescope to obtain high-resolution images and spectra with unprecedented accuracy. Each antenna has a diameter of 12 meters, making ALMA capable of detecting the smallest details in the structure of protostars and their surrounding areas. One of ALMA's most impressive achievements is its ability to observe the formation of protoplanetary disks around young stars. These disks are the birthplace of planets and provide unique information about the processes leading to the formation of planetary systems like our solar system. By using ALMA, scientists can analyze the chemical composition of these disks, determine their temperature and density, and track the movement of gas and dust. For example, ALMA has allowed the detection of molecular hydrogen, H2, carbon monoxide, CO, and methanol, CH3OH, in protostellar disks, with an accuracy of 10 circumflex 10. The temperature of the gas and dust can be measured with an accuracy of a few kelvins, while the density can be determined with an accuracy of 10 circumflex 8 particles per cubic centimeter. This not only helps us understand how planets form, but also what conditions are necessary for life to emerge on them. Where does our galaxy fit into this vast cosmic scale? The universe is astonishing in its scale and grandeur. Estimates suggest that the observable universe contains approximately 100 billion galaxies, each of which may contain between 10 million and 1 trillion stars. Our own galaxy, the Milky Way, contains about 100 billion stars, and many of them may have planets similar to our own. One of the most distant known objects in the universe is GNZ 11. This galaxy is located about 13.4 billion light-years away from us, meaning the light we see from it began its journey to Earth just 400 million years after the Big Bang. GNZ 11 allows scientists to peer into the very early infancy of the universe, providing crucial data about its formation and evolution. Distances in space are measured in light years, which is the distance light travels in 1 year, about 9.46 trillion kilometers. In comparison, The distance from Earth to the Sun is approximately 150 million kilometers, or 1 astronomical unit, AU. Thus, the closest star to us, Proxima Centauri, is about 4.24 light-years away, or roughly 268,000 AU. In addition to galaxies, the universe contains a vast number of other objects such as quasars, black holes, pulsars, and intergalactic gas. Quasars, for instance, are among the brightest objects in the universe. They are located at the centers of galaxies and are powered by massive black holes. Some quasars are more than 12 billion light-years away, making them important beacons for studying the early stages of the universe. The Hubble Space Telescope, operating in Earth's orbit since 1990, has made numerous discoveries, including detailed images of distant galaxies and quasars. The new James Webb Space Telescope, launched in 2021, is capable of observing even further and deeper, including in the infrared spectrum, which will open new horizons for astronomical research. The vastness of the universe and its incredible variety of objects continue to amaze and inspire scientists and astronomy enthusiasts around the world. What technologies and methods help scientists explore and survive in such extreme conditions? Space is an environment that impresses with its extreme conditions, making it extremely hostile to life as we know it. One of the most important aspects that defines the uniqueness of space is the vacuum. Unlike Earth, where air density is about 1 kilogram per cubic meter, in interplanetary space, the density of matter is extremely low, with less than 1 particle per cubic centimeter. This means that there is almost no air in space, and the pressure is close to absolute zero, making breathing impossible without special equipment. Temperature conditions in space are also extremely harsh. There is no atmosphere in space to retain heat, so temperatures can vary widely depending on whether an object is in shadow or under direct sunlight. For example, the temperature on the surface of the Moon can range from -173 degrees Celsius at night to +127 degrees C during the day. In interstellar space, far from stars, the temperature drops to -270 degrees Celsius, which is close to absolute zero. In addition to temperature conditions, radiation in space poses another serious threat. Outside Earth's protective magnetic field, astronauts are exposed to cosmic radiation, consisting of high-energy particles such as protons and heavy element nuclei, as well as radiation resulting from solar flares. On the International Space Station, ISS, the level of radiation is hundreds of times higher than on Earth's surface. This requires careful monitoring and protection of the crew using specialized shielding materials and structures. Extreme gravitational forces also exist in space. In black holes, for example, the force of gravity is so strong that neither light nor matter can escape its influence. The vacuum of space and extreme temperatures create unique conditions for materials. The vacuum can cause outgassing of materials, leading to their degradation over time. In particular, lubricants used on Earth do not work in a vacuum, and spacecraft require special lubricants and coatings that can withstand the extreme conditions of space. Temperature fluctuations can cause thermal expansion and contraction of materials, which can lead to structural damage. Existence in microgravity conditions, as on the ISS, also presents significant challenges for human health. Prolonged exposure to microgravity can lead to muscle atrophy and loss of bone mass, changes in the cardiovascular system, and other physiological effects. To combat this, astronauts engage in daily physical exercises and undergo regular medical checkups. While the health of astronauts in space requires careful monitoring, at the other end of the scientific spectrum, black holes are among the most mysterious and fascinating objects in the universe. Black holes possess such strong gravitational force that neither light nor matter can escape their pull. The formation of black holes is related to the collapse of massive stars at the end of their life cycle, when the star exhausts its nuclear fuel and its core compresses into an extremely dense state. One of the most well-known types is stellar mass black holes. They weigh between several and dozens of solar masses. Supermassive black holes, which can have masses millions or even billions of times greater than the Sun, are located at the centers of most large galaxies, including our Milky Way. The black hole Sagittarius A*, located at the center of our galaxy, has about 4 million solar masses. The gravitational force of black holes is so great that they warp the space and time around them. The proximity to the event horizon, the boundary beyond which nothing can escape, causes extreme distortions of space-time. Gravitational tidal forces in this area are so strong that they can stretch and tear apart objects that come too close in a process known as spaghettification. But how do they affect galaxy formation? One of the key questions that intrigues scientists is the role of black holes in the formation and evolution of galaxies. Could supermassive black holes play a central role in shaping galactic structure? Observations show that the mass of a supermassive black hole at the center of a galaxy correlates with the mass of the galactic bulge, the central bulging area of the galaxy. This may indicate a close relationship between the processes of galaxy growth and formation. Black holes also play an important role in regulating galactic activity. They can consume vast amounts of matter, causing bursts of high-energy particles and radiation. These outflows can affect the interstellar medium, heating it and inhibiting the formation of new stars. For example, in some active galaxies, known as active galactic nuclei, AGN, powerful jets are emitted by black holes that can stretch across thousands of light years. Gravitational waves produced by mergers also provide unique opportunities to study these objects. In 2015, the LIGO Gravitational Wave Observatory first detected such waves, confirming one of Einstein's key predictions of general relativity. Since then, several black hole merger events have been observed, opening a new window into the study of the universe and allowing the investigation of properties such as mass and spin. Additionally, there are hypotheses about the existence of so-called primordial black holes, which might have formed shortly after the Big Bang from dense regions of the early universe. These hypothetical black holes could explain some observed phenomena, such as dark matter. However, their existence has not yet been confirmed by observations, and it remains one of the many mysteries of the cosmos. Exoplanets, or planets outside our solar system, are one of the most fascinating and actively researched areas of astronomy. Since the discovery of the first exoplanet in 1992, scientists have found over 5,000 such worlds, each unique in its characteristics and conditions. One of the most interesting aspects of exoplanets is their diversity. They range from gas giants similar to Jupiter to rocky planets the size of Earth, or even smaller. For example, the exoplanet 55 Cancri E, located about 40 light-years away from us, is a rocky planet, but conditions on its surface are completely inhospitable to life as we know it. The temperature on the planet's daytime side reaches 2,400 degrees Celsius, making its surface molten lava. On the other hand, there are many planets in the so-called habitable zone of their stars, an area where conditions might be suitable for liquid water and possibly life. One such world is the exoplanet Kepler 452b, located about 1,400 light-years from Earth. It orbits a star very similar to our Sun and is in a zone where water could exist in liquid form. An intriguing object of study is also the TRAPPIST-1 system, where 7 exoplanets have been discovered, 3 of which are in the habitable zone. These planets orbit an ultra-cool red dwarf only 39 light-years from Earth. What makes the TRAPPIST-1 system particularly intriguing is the close proximity of the planets to each other. If you were standing on one of these planets, the other planets would be visible in the sky as clearly as the Moon is from Earth. Exoplanets can also have conditions radically different from those on Earth. The gas giant HD 189733b, located 64 light-years away, has winds reaching speeds of up to 8,700 kilometers per h and rain made of glass droplets flying horizontally due to the strong winds. These exotic conditions make HD 189733b one of the most interesting objects for study. Another remarkable world is the planet Gliese 1214b, which is an aquatic world. Located about 48 light-years away, this planet is 3 times the size of Earth and is thought to be completely covered by water. Scientists believe that Gliese 1214b may have a deep ocean beneath a thick atmosphere, making it a potential candidate for the search for life. Modern telescopes, such as the James Webb Space Telescope, provide scientists with the ability to study the atmospheres of exoplanets in detail. Through spectroscopy, it is possible to determine the chemical composition of the atmosphere, including the presence of water, methane, carbon dioxide, and other substances, which helps us understand the conditions on these distant worlds. Exoplanets continue to expand our knowledge of the universe and its potential for life. Each new discovery brings us closer to answering one of the most fundamental questions: are there other habitable worlds in the vast expanses of space? The concept of time in space is significantly different from the familiar time on Earth. On cosmic scales, time can be distorted by gravitational fields, especially near massive objects such as black holes. This phenomenon, known as gravitational time dilation, is predicted by Albert Einstein's general theory of relativity. Gravitational time dilation occurs because massive objects warp the space-time around them. The stronger the gravitational field, the slower time passes for an observer within that field. Near black holes, this distortion becomes extreme. If a hypothetical astronaut approaches the event horizon of a black hole, time for them will pass much more slowly compared to an observer at a safe distance. Thus, if the astronaut spends a few hours near a black hole, years or even decades might pass on Earth. This effect is not limited to black holes. Significant time distortions are also observed near other massive objects, such as neutron stars or white dwarfs. Even our Earth causes a minor but measurable gravitational time dilation. Clocks on the Earth's surface run slightly slower than those at several kilometers above the surface. Studying gravitational time dilation has important practical applications. Global Positioning System (GPS) satellites orbiting Earth must adjust their clocks to account for this effect, to ensure accurate navigation data. Without such adjustments, GPS devices on Earth would have errors of several kilometers. Understanding how time is distorted by gravity also helps scientists study extreme cosmic phenomena and test the fundamental postulates of relativity theory. Observations of time behavior in various gravitational fields continue to expand our knowledge of the universe's nature and its fundamental laws, highlighting the remarkable interplay between space, time, and gravity. But the interest doesn't stop there. What other challenges do astronauts currently face? Space debris is one of the most pressing issues. It includes fragments of old satellites, rocket parts, debris from collisions, and other non-functional objects orbiting Earth. As of 2023, the number of such objects was estimated to be over 34,000, each larger than 10 centimeters, along with hundreds of thousands of smaller particles that could cause significant damage upon impact. One of the major threats posed by space debris is the risk of collisions with active satellites and spacecraft. Even small particles traveling at speeds of up to 28,000 kilometers per hour can cause critical damage. For example, in 2009, a collision between the non-functional Russian satellite Cosmos 2251 and the operational American communication satellite Iridium-33 resulted in thousands of new debris fragments. Space debris also presents a serious threat to crewed missions and the International Space Station, ISS. The ISS crew regularly performs maneuvers to avoid potentially hazardous objects. In 2021, the station had to change its orbit 3 times to avoid collisions with space debris. Various strategies and technologies have been developed to address the space debris problem. One method involves using lasers to remove small debris fragments from orbit by vaporizing them. Larger projects include the development of cleanup satellites capable of capturing and deorbiting large objects. For example, the Japanese company Astroscale is developing technologies to capture and remove non-functional satellites from orbit. The international community is also actively discussing regulations and control measures. The United Nations, UN, and the Committee on the Peaceful Uses of Outer Space, COPUOS, are working on standards and recommendations for managing space debris. One such document is the Space Debris Mitigation Guidelines, which includes recommendations for designing satellites with the capability for safe deorbiting after their mission ends. Another important aspect is cooperation between countries and private companies. Joint efforts in monitoring and predicting orbital debris movement enable more effective risk management and collision prevention. Programs such as the European Space Operations Centre, ESOC, and the US Space Surveillance Network, SSN, play a key role in tracking and informing satellite operators about potential threats. Despite efforts to address the issue, the amount of space debris continues to grow. The active development of the space industry and the launch of increasing numbers of satellites, such as those for internet coverage, raise the risk of new debris fragments forming. Space debris poses a significant threat to satellites, space missions, and crewed flights. Solving this problem requires a comprehensive approach, including technological innovations, international cooperation, and stringent regulation. Only through joint efforts can humanity tackle this challenge and ensure the safe and sustainable use of outer space in the future. But one of the most exciting questions for humanity remains open. Could there be life in other parts of the universe? The scientific community is actively exploring the potential for extraterrestrial life using the most advanced technologies and methods. Today, the search for life beyond Earth is being conducted in several key areas. One of the most promising locations for searching for life within our solar system is Europa, a moon of Jupiter. Scientists believe this icy world has a subsurface ocean hidden beneath a thick layer of ice. Europa's ocean may contain more water than all of Earth's oceans combined and could possess the necessary conditions for microbial life. In 2024, NASA plans to launch the Europa Clipper mission, which will study Europa's surface and subsurface ocean, look for signs of hydrothermal activity, and assess its habitability. Another object of interest is Enceladus, a moon of Saturn. The Cassini mission discovered geysers ejecting water vapor and organic molecules from beneath Enceladus's icy surface, indicating the presence of a subsurface ocean with potentially habitable conditions. Studies suggest that Enceladus's ocean may be chemically balanced and contain key ingredients for life. Extraterrestrial life might also exist on exoplanets located beyond our solar system. Scientists use space telescopes to study exoplanet atmospheres and search for biosignatures, chemical signs that could indicate the presence of life. These studies focus on detecting substances like oxygen, methane, and water, which are key components for life. One of the most exciting exoplanets in this context is Proxima Centauri b, located just 4.24 light-years from Earth and orbiting our closest star. Proxima Centauri b is in the habitable zone of its star, where temperatures might allow for liquid water on its surface. Despite the intense radiation from its parent star, scientists hope the planet may have an atmosphere capable of shielding potential life. In parallel with studying specific objects, efforts are underway to search for radio signals from extraterrestrial civilizations. Projects like Breakthrough Listen use powerful radio telescopes to scan the skies for artificial signals that might indicate intelligent life. Although no convincing evidence has been found yet, these searches continue to inspire and capture global attention. Modern astrobiological research includes experiments that model conditions that might exist on other planets. Laboratories on Earth attempt to recreate conditions similar to those on Mars or in the subsurface oceans of moons to understand what forms of life might exist there and how they could be detected. The possibility of life existing elsewhere in the universe opens vast prospects for science and philosophy. If we ever find evidence of extraterrestrial life, it will transform our understanding of humanity's place in the universe and raise many new questions. Stay with us to keep up with the latest news and discoveries in this exciting field of science. Subscribe to our channel and follow the updates to ensure you don't miss any important news from the world of space and astronomy.